The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Last time you talked about the first law of thermodynamics, and you talked about isothermal expansions, the Joule expansion. You saw a very important result, which is that for an ideal gas, the energy content is only dependent on the temperature and nothing else. Not the volume, not the pressure, just cares about the temperature. So if you have an isothermal process for an ideal gas, the energy doesn't change. Q plus W is equal to 0 for any isothermal process. And you also saw that du then could be written as CV dt for an ideal gas always. This is not generally true. If you have a real gas and you write du is CV dt and your path is not a constant volume path, then you're making a mistake. But for an ideal gas, you can always write this. And this turns out to be very useful to remember. OK. Now, most processes that we deal with are not constant volume processes. Right? So energy, which has this wonderful property here, du is CV dt for constant volume process, which happens to be equal to dq constant volume, because there's no change, there's no work if you've got a constant volume process. So du here is a very interesting quantity because it's related to the heat that's going in or out of the system under a constant volume process. But as I said, we're not operating usually in a constant volume environment. When I flail my arms around, I generate work and heat. This is not a constant volume process. If I'm the system, what's constant when I do this? Anybody have an idea? What's the one function of state? I'm the system, the rest of the surrounding. What's the one function of state that's constant when I'm doing all my chemical reactions to move my arms around? Temperature? Pressure, right. Pressure is constant. What is the pressure at? 1 atmosphere, 1 bar. So the most interesting processes are the processes where pressure is constant. When I have a vial on my bench top and I do a chemical reaction in the vial, and it's open to the atmosphere, the pressure is constant at 1 atmosphere. When you've got your cells going in your Petri dish, the pressure is constant at 1 atmosphere. Okay, even if they're evolving gas, pressure is constant. So we'd really like to be able to find some sort of equation of state, or some sort of rather function of state, that's going to relate the heat going in or out of the system with that function of state. Because this isn't going to do it. du only relates to the heat under constant volume. And the heat is a really important thing to know. How much heat do you need to put into a system, or how much heat is going to come out of a system when something is happening in the system? Right? This is a really important quantity to know. You're boiling water or whatever. You want to know how much heat is going to go in, how much heat you need to boil that amount of water under constant pressure. And this is where enthalpy comes in. You've all heard of enthalpy. H. We're going to write it as a function of temperature and pressure. And the reason why enthalpy was invented was exactly for that reason, because we need some way to figure out how to relate the heat coming in or out of a system under a constant pressure process, because it's so important. And I should add, and also under reversible work, where the external pressure is equal to the internal pressure. OK, so we're going to define enthalpy as U plus PV. These are all functions of state here, so H is a function of state. And we're going to see now how this is indeed related to the heat flow in and out of a system if you have a constant pressure reversible work process. Okay, well, let's take a system under constant pressure, T1, V1, going to a second. This is the system. So let me write the system here. And it's more dramatic if the system is a gas, P T2, V2. And let's look at what happens to these functions of state, to H, to U, under this transformation. OK, so let's look at delta U. Delta U is Q plus W. That's the first law. And this is a constant pressure path. So now I can write this Q is actually Q under constant pressure. Little p means the path is a constant pressure path. And I'm doing reversible work. So that W is minus P dV, where P is the pressure inside the system, minus P delta V. Right? Rearrange that. Delta U is plus P delta V is equal to QP. All right, so this is the heat flowing in or out of the system, and these are all functions of state. Right? This depends on the path. It tells you right here the path is constant pressure. These don't depend on the path. Right? V doesn't care how you get there. U doesn't care how you get there. In this case, P is a constant because the path is constant, so we can bring the P inside. Delta U plus delta PV, it's QP. Take this delta outside again. Delta of U plus PV is equal to QP. And there you have it. There's the H right there, the U plus PV. Delta H is equal to QP. And this is the reason why enthalpy was invented and why it's so important. Because we want to know this. So this is for a finite change. If you want to have an infinitesimally small change, you end up writing dH is dq sub p. It's not always equal to the heat. It's only equal to the heat if your process is constant pressure reversible work. OK, so this is the kind of concept that needs to be branded into your brain, so that if I come into your bedroom in the middle of the night and I whisper to you delta H, you should wake up and say QP, right? Heat under constant pressure reversible work. Should become second nature. This is where the intuition comes from. This is why people write tables and tables of delta H's. Why you have delta H's for all these reactions. Because it's basically the heat. And the heat is something we can measure. We can control. We can figure out how much heat's going in and out of something. This is what we're interested in. OK, so last time you looked at any questions on this first? Yes?
What was the transformation from the P delta V to the delta PV? What was the reason behind that?
P is constant here.
OK.
It's constant pressure. OK, so now last time you looked at the Joule expansion to teach you how to relate derivatives like du dv. Du dv under constant temperature, du dt under constant volume. You use the Joule expansion to find these quantities. And these quantities were useful because you could relate then the slope of changes with respect to volume or temperature of the energy with respect to quantities that you understood, that you could measure. And we're going to do the same thing here. So if we take as our natural variables for enthalpy to be temperature and pressure, and we have some sort of change in enthalpy, dH, and it's going to be related to changes in temperature and pressure through the derivatives, dH through the slope of the enthalpy in the t direction, keeping pressure constant, dt, plus the slope of enthalpy in the pressure direction, keeping the temperature constant, dP. And these are knobs that we can turn. We can change the temperature. We can change the pressure. These are physical knobs that are available to us as experimentalists. And so when we turn these knobs on our system, we want to know how the enthalpy is changing for that system, because eventually they will tell us it may be things about how heat is changing further on. Okay? But in order to relate turning these physical knobs to this quantity here, which we don't have a very good feel for, we've got to have a feel for the slopes. If I keep the pressure constant, I change the temperature, what does that mean? What is dH dt? If I keep the temperature constant and just change the pressure, dH is going to change. But how is it going to change? What does this mean in terms of something I can physically understand? So that's the program now for the next few minutes. What are these quantities? What is dH dt as a function? Keeping pressure constant. What is dH dP? Keeping temperature constant. All right, let's start with the first one, dH dt, keeping the pressure constant. And we're going to look at a reversible process. To help us out, but the result is going to be independent of whether or not we have a reversible process or irreversible process. Constant pressure, that means dP is equal to 0. Okay? So for reversible process, constant pressure, what do we know? Okay, this is already branded in your brain, right? Reversible process, constant pressure, dH is dQ. So we can write that down. dH is dQ, constant pressure. That's by definition of enthalpy. That's why we created enthalpy. What else do we know? Well, we can go look up here, looking at the differential. There's no approximations here. This is just inequality. I have a constant pressure process. This term here is equal to 0. That means that dH is also equal to dH dt, constant pressure dt. All right, so now I've got what dH dt is under constant pressure. dH is equal to this, and it's also equal to this. Right? These two are equal to each other. Now, I know how to relate the heat flow to temperature change through the heat capacity. Right? dQ, constant pressure, is the heat capacity. And I have to tell you the path for the heat capacity. So it's C sub P, the heat capacity under a constant pressure path, dt. Right? So these two are equal to each other. So these two are equal to each other as well, which tells me that this derivative, dH dt, constant pressure, is Cp. So now I have my first of my two slopes in terms of something that's related to my system, the heat capacity of the system, something I can measure and I can tabulate. And when I turn my dt knob here, I know what's going to happen to the enthalpy. Okay, so this is the first. This is the easy one. So it's very similar to what we saw with the volume and the energy, where du dv under constant temperature was equal to Cv in this case here. Right. And you're going to find that there's a lot of these analogies between energy and enthalpy. You just change volume to pressure, and basically you're looking at enthalpy under a constant. Anything that's done under constant volume path for energy, there's the same thing happening under constant pressure path for enthalpy. So you can guess the answer usually that way. Okay, so now we have the other one, dH dP constant temperature. How do we relate this to something physical? Well, it's going to be an experiment, very much like the Joule experiment. The Joule experiment was a constant energy experiment. Right? Here we're going to have to find a constant enthalpy experiment. And that is going to be the Joule-Thomson experiment. That's going to extract out a physical meaning to this derivative here. Okay, the Joule-Thomson experiment. This is going to get us dH dP constant temperature. What is this experiment? You take a throttle valve, which consists of some sort of porous plug between two cylinders that is insulated. So there's insulation here, insulation on the bottom. It's like think of a tube, large tube, insulated tube, with a bunch of a frit inside here, okay, which prevents flow of gas, which slows down the flow of gas from one side to the other. Right? It's a blockage in this tube here. Then you put two pistons, one on that side here, and one on this side here. And the external pressure here, we're going to call that P1. The external pressure here, we're going to call that P2. And we're going to do it slowly enough that the pressure on this side of the cylinder is in equilibrium with the external pressure. And the pressure on this side of the cylinder is in equilibrium with this pressure, but not so slowly that these two are in equilibrium with each other. Okay? So this is restricting the flow. So there's some sweet spot here when I'm pushing slowly enough here that the pressure here is equal to that one, but not so slowly that the airflow from here to here is fast compared to how fast I'm pushing. Right? You got the picture here? Any questions on that? All right. Then as I push through, I'm going to start with all my gas on this side, and at the end, I'm going to have all the gas on the other side. Let me first ask you this. Is this a reversible or an irreversible process? Right? Let me add one more piece of data here, which I said in words, but which is actually important to write down if you're doing the problem. Is this a reverse? Any guesses? How many people vote for that this is a reversible process? I've got 1 vote back there, 2 votes, 3 votes, 4 votes. Anybody else? How many people vote this is irreversible? It's about a tie, and everybody else doesn't know. All right, I'm going to give you 10 seconds, 15 seconds to make up your mind. You're not allowed to be on the fence here. You've got to decide, all right? You can talk to your neighbors, do a little bit of thinking, and I'm going to give you 10 seconds to figure this out, what your vote is for that. All right, let's try again. How many people vote that this is reversible? That looks like a majority to me. Irreversible, let's look at the show of hands. All right, so this is the majority here. Good thing physics doesn't work on the rule of the majority. Otherwise, we'd be in big trouble. Well, let's log through that. I'm sorry to say that this is the wrong answer. OK, why is that the wrong answer? Well, just think about it. You're pushing through here. P1 is greater than P2. What does it mean for a process to be in equilibrium? or reversible. It means that at any point, you can reverse the direction of time, and it will look fine. Right? So now I'm pushing on this plug here with P1 greater than P2. I'm pushing, I'm pushing, I'm pushing. P1 is greater than P2. Then I want to reverse direction of time. I want the arrow of time to go so that the gas goes from P2 to P1. P2 is less than P1. Is that going to work out? If P2, the pressure in P2 is less than the pressure in P1, is the gas going to want to go from P2 to P1 and the whole thing reverse back? You've got to put more pressure on one side than the other if you want to push that gas through the throttle, right? So this is where the time scale issue comes into play. I said, let's do this slowly enough that this P1 is in equilibrium with this P1, but not so slowly that this pressure is in equilibrium with that pressure. If I do it really, really slowly so that everything is reversible, well, I won't be able to do it because P1 and P2 are different. But suppose that I fix my pistons here with P1 greater than P2, and I don't touch it, eventually P1 will be equal to P2. I'll come to some sort of equilibrium. So this is a system which is out of equilibrium. If I stop, if I move slowly, if I move more slowly, then these two will want to equilibrate. Right? So this is an irreversible process. The Joule-Thomson experiment is irreversible. OK, important. If you are part of this group here, think about it and make sure you understand that. All right, so this is the experiment. Now, what are we doing with that? The initial state, let's look at what we're doing here. So initially, we're going to have our piston. There's the plug sitting here. Our piston on the right side here, fully out, and the piston on my right side, your left side, fully inside. There's no gas on that side here. So there's P2 sitting here. There's P1 sitting here, and all of the gas is sitting on that side of the plug. Then after we're done with the experiment, we'll have transferred all of the gas from one side to the other. P1 here, P2 sitting here. OK. And there's going to be some volume V2 and some volume V1 that are not necessarily the same, especially since the pressures are different. Right? We don't know yet about temperature, so I don't know what to say about these volumes because I don't know what the temperature is going to do. OK, so let's go through this and see what we would do, which is to calculate the heat and the work. This is well insulated. So what is the, let's do the first one here. What's Q for this process here? Anybody? 0, right. This is an adiabatic process. It's well insulated. Heat is not going in or out. Adiabatic. Q is equal to 0. So all we need to find out is the work now. Let's divide it up into the two sides, the work going on the left-hand side, my left-hand side, or your left-hand side, and the work going on the right-hand side. So let's first look at the left-hand side. OK? So W, first of all, work is being done to the system on the left-hand side here. I'm pressing on the gas. So I expect that to be a positive number. The pressure is constant, P. The V goes from V1 to 0. So we write down as P1, V1. Okay. On the right-hand side, the work, let's call this left-hand side. Let's call this right-hand side. Here, there's an expansion going on. So the system is doing work to the external world. This piston is being brought out. So we expect the work to be negative. And we start out with 0 volume. We end up with a volume of V2, and the external pressure is constant at P2, minus P2 V2, minus P delta V. So the total work is the work from the left-hand side plus the work on the right-hand side, which is P1 V1 minus P2 V2, which I can rewrite as minus delta PV. Okay? Delta PV is P2 V2 minus P1 V1. It's the pressure volume multiplied together at the final state minus pressure volume from the initial state, with the minus sign here because it's the negative of that. All right, what is delta U? Delta U is Q plus W. Q is 0. Delta U is just W. So this is also delta U. Delta U is minus delta PV for the process. OK, delta H is delta of U plus PV. By definition, that's how we define enthalpy up here. H is U plus PV. Delta H is delta of U plus PV, which is equal to delta U plus delta PV. Now, delta U is minus delta PV. So I have minus delta PV plus delta PV. This is equal to 0. So this irreversible process, this Joule-Thomson process, is a constant enthalpy process. Delta H for this process is equal to 0. Adiabatic Q equal to 0. It's also delta H equal to 0. Okay. The two didn't necessarily follow because, remember, delta H is dQ sub P is only true for a reversible constant pressure process. This is an irreversible process. So a priori, this was not necessarily true. It turns out after you do all the math, it turns out to be delta H equals 0. All right, so this is the experiment. How do we go from that experiment to the terms that we're trying to get, these slopes? Remember, we're trying to get delta H. We're trying to get dH dt, constant pressure, and dH dP, constant temperature. Okay, these are the two things we're trying to get here. OK, so let's write down what we know here. I'm missing something. Oh, we already know one thing. We already know this guy here. We already did that. Okay, dH dt, constant pressure, is Cp. That was the easy one. So we already know that. So now we can write our differential dH as Cp dt plus dH dP, constant temperature dP. Okay, now we want to find out what this guy is here. Now, for this experiment, this is a constant enthalpy experiment. For the Joule-Thomson experiment, this is equal to 0. So I can rearrange this to get this dH dP in terms of things that I can either measure, like the heat capacity, or that I have control of, like dt and dP. Right? So in this case, dH dP, constant temperature, is minus Cp dt dP. And this is under constant temperature. No, not constant temperature. Whatever the for that experiment is. Constant. Okay. For that experiment, the constraint, so we need a constraint here, right? We need a constraint here. The constraint isn't constant temperature, because temperature is going to be changing. It's not constant pressure because we have a delta P going on. It's not constant volume either. The constraint is the constraint of the experiment. And the constraint of the experiment is that the enthalpy is constant. So the constraint we have here is a constant enthalpy. It's a constant enthalpy process that we're looking at. This we can do experiments on. It's tabulated in books. And this we can measure in the experiment. Delta P here is the change in pressure from the left side to the right side. And we can put a thermometer, measure the temperature before the experiment, and measure the temperature after the experiment. So this is something we can measure. So now we have this derivative in terms of physical quantities, things that we can measure, things that we can relate to the properties of the substance that we're doing the experiment on. So this is basically delta T, delta P in the Joule-Thomson experiment. And so Joule and Thomson did these experiments, and they measured lots of gases, and they found that, in fact, this was something they could measure. Sometimes it was positive, sometimes it was negative, and it was an interesting number. And so they defined then, after many experiments, the limit of this delta T, delta P, and the limit of delta P goes to 0 as the Joule-Thomson coefficient. So basically dt dP under constant enthalpy is equal to mu, by definition, Joule-Thomson, where mu Joule-Thomson is the Joule-Thomson coefficient, just like you saw last time, eta sub j was the Joule coefficient for dt dV under constant energy. So there's, again, total analogy here between what we're doing with enthalpy to what you did last time with energy. Replace P with T and H with U, basically. You flip those two and you get the same thing. OK, so now we have dH dt is equal to Cp, and we can also write then dH dP under constant temperature is equal to minus Cp mu Joule-Thomson. We have our two derivatives in terms of physical quantities, which is going to allow us then, whenever we have a change, to go back and when we have a change where we adjust the temperature and the pressure, we'll be able to know what the enthalpy change is. OK, now let's take two cases. Let's first start talking about ideal gases. So last time you saw that for an ideal gas, the energy only cared about the temperature. It didn't care what the volume was doing. du dV under constant temperature was equal to 0 for an ideal gas. And by analogy, we expect the same thing to be true here, because enthalpy and energy have all this analogy going on here. So let's look at an ideal gas. So for an ideal gas, we saw that U was only a function of temperature. We also have the equation of state for an ideal gas. PV is equal to nRT. We can write our definition of enthalpy. H is U plus PV. This only depends on the temperature. PV is equal to nRT. So we have U only depends on the temperature plus nRT. The only variable now on this side is temperature. Pressure and volume have dropped out. Right? So enthalpy for an ideal gas only cares about temperature. Pressure has dropped out of the picture completely here. Okay? So there's no P dependence here. H for an ideal gas is only a function of temperature. This is not true for a real gas, fortunately, but it's true for an ideal gas. So for an ideal gas, then, dH dP under constant temperature, that has to be equal to 0, because temperature is constant. H only cares about temperature. And that's equal to 0. And if that's equal to 0, that means that the Joule-Thomson coefficient for an ideal gas is also equal to 0. We're going to actually prove this later in the course. Right now, you're taking it for granted. Right now, we told you Joule did all these experiments, and he found out that for an ideal gas, that the limit in an ideal gas case was that the A was equal to 0. Therefore, from experiments, U is only a function of temperature for an ideal gas. And therefore, from these experiments, we come out with delta H dH dP is equal to 0. The Joule-Thomson coefficient is equal to 0. Later, we're going to prove it exactly. Okay. But right now, you're going to have to take it for granted. So if the Joule-Thomson coefficient is equal to 0, just like we wrote du is Cv dt for an ideal gas, we're going to have dH is Cp dt for an ideal gas as well. Right? dH is Cp dt. This term goes away. dH is equal to Cp dt. That's the only thing that's left behind. So if you know the heat capacity, you know the change in temperature, you know what enthalpy is doing for an ideal gas. Right? This needs to be stressed that this is the ideal gas case. Now, regular gases, real gases, fortunately, as I said, don't obey this. This is important because we use this all the time for when we do technology. Okay. One example of Joule-Thomson coefficient being not equal to 0 for a real gas that you've likely experienced is if you take a bicycle pump. You take a bicycle pump, and you're pumping up your tire, and you're working pretty hard, so you're getting hot. But if you touch the valve going into your tire, which basically measures the temperature of the air going into your tire, that is getting hot. Right? So if you've got to pump that tire really a lot, then you're going to really feel a lot of heat there. The compression of basically it's an adiabatic compression. You're taking the air inside of the pump and you're compressing it. You're doing so fast that there's not enough time for heat to come out of the gas that's inside the pump towards the walls of the pump. Okay? So your time scale is just fast enough that this is basically an adiabatic compression. You're compressing it really fast, right? So you're changing the pressure. You're changing the pressure, and the temperature is going up. dt dP is positive. Right? dt dP is positive. dt dP is positive. Well, that's mu jt. dt dP is mu jt. Right? So for a real gas like air, this is a positive number. It's not 0. Air is not an ideal gas. It's one simple example of the fact that mu jt is not 0 for real gases is how we are able to liquefy things like hydrogen and helium by compressing them and pushing them through a nozzle. And the expansion through the nozzle cools the gas. Right? In this case here, it wouldn't happen if it was an ideal gas. Or in many kinds of gas refrigerators, where you push a gas through a nozzle close to room temperature, what you find is that the gas coming out on the other side under lower pressure is cooler than the gas that went through on that side. Real refrigerators actually work with liquids that go into gases, so use the latent heat of the liquid. So it doesn't really work like a Joule-Thomson expansion. So this is real. Unlike the Joule coefficient, which is very small, so that most gases have tiny Joule coefficients. So if you do a Joule experiment, you hardly measure a temperature change. With real gases, here you do actually measure it. You can feel it with your finger on your temperature on your bicycle tire. Okay, so we're gonna see this using a van der Waals gas. Let's look at a van der Waals gas and see what happens in the van der Waals gas. Any questions first on what we've been talking about, the Joule-Thomson experiment, constant enthalpy process? Okay, so let's take our van der Waals gas. Remember, the equation of state for van der Waals gas is not PV is equal to nRT, but P plus the attraction term, and then V minus the excluded volume term is equal to RT. Two parameters. This is the attraction between two atoms or molecules in the gas phase. This is the repulsion, not the repulsion. This is the fact that they occupy a finite volume in space because they're little hard spheres in this model here. Okay. In a few weeks, you're going to find out that we can calculate dH dP from this equation of state. And you're going to find that dH dP from that equation of state is proportional to B minus A over RT. Okay? This is going to be probably a homework at some point to do this. For now, let's take it for granted. Let's take it for granted that we know how to calculate this derivative from an equation of state like this. Okay? But now we're going to use that. Okay, so since dH dP under constant temperature is proportional to minus mu jt, then we have that dt dP under constant enthalpy then is related to the negative of this, A over RT minus B. All right, this is how the temperature changes when you have a pressure change. So when you do an expansion or a compression, my adiabatic compression of my bicycle pump is dt dP. Right? Or when I do an expansion of hydrogen or helium at low temperature through a Joule-Thomson experiment when I want to liquefy hydrogen or helium. I want to cool a gas through a Joule-Thomson experiment. What temperature do I have to be at? So this tells you that you have to be careful what temperature you're at, because depending on how big this temperature here is, you could either have a negative dt dP if this first term is small enough, meaning if temperature is very high, then you end up with a negative term. If the temperature is very small, then 1 over temperature is large, and the first term wins, and you have a positive number. So there's some special temperature which is going to depend on the gas, where the first term is going to be equal to the second term, where the Joule-Thomson is 0, where it's going to behave like an ideal gas. So when that is the case, we're going to call that temperature the inversion temperature, or TINV. We call that inversion because on one side, you end up cooling if you compress, and on the other side of that temperature, you end up heating if you compress. Okay, so there's some temperature, T inversion minus B, where the gas behaves like an ideal gas. The Joule-Thomson coefficient is 0. And that inversion temperature, you can solve for it. Inversion temperature is equal to A over R times B. Okay. So when you're at that temperature, everything looks like an ideal gas as far as the enthalpy changes are concerned. Now, if you're at the temperature which is higher than the inversion temperature, in that case here, A over RT is small compared to B. And this is going to turn out to be negative. Right? So if you had a high temperature, this is small compared to B. You're negative, which means that dt dP, constant H, is then less than 0. Okay. So that means that if you compress something, it's going to cool. The temperature rises when the pressure drops, right? Or in this case here, if I do my Joule experiment, delta P is negative. P2 is less than P1. That means that delta T is positive, right? So in this experiment here, this side is going to heat up. Right? So for materials where T inversion is lower than room temperature, then you would end up heating up in this expansion. You're basically expanding the gas from one side to the other, and the expansion causes the temperature to rise. If T is less than T inversion, you have the opposite case, and dt, dP is greater than 0. So in this experiment here, delta P is less than 0. You need to have this whole thing greater than 0. So delta T is less than 0 as well. So if you're below the inversion temperature and you do the Joule-Thomson experiment, you're going to end up with something that's colder on this side than that side. Ideal gas, it would be the same temperature. Right? But now, so this is where the refrigeration comes in. Right? So if you take a gas and you're below the inversion temperature and you make it go through this irreversible process, the gas comes out colder from that side than that side. So the work that you're doing to expand, to go through this experiment, ends up cooling the gas. OK, for most gases, T inversion is much greater than 300 degrees Kelvin, much greater than room temperature. For most gases, if you do this experiment at room temperature, you end up cooling the gas. And you can cool it measurably, which is why also your bicycle pump, you push down, you compress. This is an expansion here. You're expanding from this side to that side. Bicycle pump, you're compressing the gas, which is the opposite. You end up heating up the air in your bicycle pump, in your compression. There are two exceptions to this rule that most gases have a T inversion which is greater than 300 degrees Kelvin, and that's hydrogen. The T inversion for hydrogen turns out to be 193 degrees Kelvin, and the T inversion for helium turns out to be 53 degrees Kelvin. Okay. And so when there's a lot of liquid helium that's being used on campus, we use liquid helium. And so in order to make liquid helium, you can't take helium at room temperature and do this, because if you did, you would just heat it up, because the room temperature is above the inversion temperature. So Joule-Thomson would heat up the helium. So you need first to take the liquid helium and cool it below 53 degrees Kelvin before you can do the Joule-Thomson to cool it even further to make liquid helium. So you have to do it in stages. You take your room temperature liquid helium and you cool it with liquid nitrogen to 77 degrees Kelvin. Then you're not quite there yet, unfortunately, right? Then you take hydrogen and you cool it with liquid nitrogen to 77. Then you can use your hydrogen gas, do a Joule-Thomson on the hydrogen gas, which you first cool with liquid nitrogen. Liquid nitrogen 77, that's below 193. So you can do Joule-Thomson on hydrogen, cool the hydrogen to below 53. Then use your cold hydrogen to cool the helium. And then you can do the Joule-Thomson on the helium to cool it further until it liquefies. So that's what you do when you make liquid helium. All right, any questions on this lecture or any of the concepts that we talked about? OK, the last thing that we're going to do today then is to look at a relationship which is going to turn out to be very useful. And it's a relationship for ideal gases which relates the heat capacities at constant pressure and constant volume. Right. Cp, constant volume, is Cv plus R. This is very useful because often you just have lots of tables of CPs, but sometimes you want to know what the energy change is going to be for the ideal gas. And you know that du is Cv dt, not Cp dt. So you need to know what Cv is. And if this is true always, then there's a very easy way to go from one to the other. We're going to do it two ways. Today we'll do the first way, and the next time we'll do the second way. The first way is just to turn the crank on the math. And the second way is to do a little bit more imaginative about the process. Okay, let's just turn the crank on the mass. What do we know about Cp and Cv? Well, Cp, we already know how to relate it to dH dt, to the slope of the enthalpy. And we also related Cv to the slope of the energy with respect to temperature under constant volume. And we also know that H is U plus PV. Right? H is U plus PV. So we're going to take the derivative of both sides of this equation here by, with respect to temperature, keeping pressure constant. So we have dH dt, keeping pressure constant, is du dt, keeping pressure constant. You've got to keep track of what's being constant, kept constant, plus dPV dt, keeping pressure constant. dH dt keeping pressure constant, that's just Cp. And then we have du dt keeping pressure constant. The P is constant here, comes out of the equation, so we have P, and then we have dV dt. Well, it's an ideal gas. An ideal gas for dV dt for an ideal gas is equal to R over P, because PV is equal to RT, right? So dV dt is R over P. So dV dt is times R over P. The P's are going to cancel out here. Okay. So now it's very tempting at this state to say, oh, there's the answer right here. du dt is Cv. There I have it. Cp is equal to Cv plus R. Right? But even though it looks like that's the right way to do it, it's actually not right, because it turns out to be right by sort of by accident. But here you've got pressure constant. Right? Du, this is du, not H here. Du dt is only equal to Cv when the volume is constant, not when the pressure is constant. So if you're going to turn the crank on the math correctly, you're going to have to change this P into a V somehow. Because this isn't Cv, mathematically speaking. We don't know what it is yet. In order to change this from a P to a V, you have to use the chain rule. So let's use the chain rule. And then we'll be done. OK, so U is actually a function of temperature and volume, which in this case here could be a function of pressure and temperature. So if we want du dt under constant pressure, we have to use the chain rule. There's the pressure sitting right here. Okay? It's going to be du dt under constant volume plus du dv dt under constant pressure. Right? Chain rule. Right? Du dt constant pressure is the direct derivative with respect to temperature here, which is sitting by itself under constant volume, keeping this constant. But there's temperature sitting right here too. That's where that term comes from, du dv dt. Okay. Now, for an ideal gas, du dv under constant temperature is equal to 0. Okay. Doesn't care what the volume is doing. It only cares what temperature is. Temperature is constant. There's no change in energy. For an ideal gas, this is 0. It's not 0 for a real gas. Right? So this whole term disappears. And for an ideal gas, it turns out that du dt constant pressure is equal to du dt constant volume, that this is equal to Cv for an ideal gas. It wouldn't be true for a real gas. And this is a common mistake that people make for real gases to equate those two. This is only true for an ideal gas. Since it's true for an ideal gas, then we can go ahead and replace this with Cv. And then we have Cp is Cv plus R, which is what we were after, QED. OK, next time we'll do the other way of getting to the same answer.